Before spring break. Has to be before spring break because it just has to. You guys are not going to remember anything after spring break.
You're so right.
I'm not wrong. I know I'm correct. I knew it when I was in grade 12 and you had a choice, biology 12. You could write the nervous system test before the break or after the break. I chose before the break, as did the other people, right-thinking people in the class. All the people who are like, oh no, I want more time to study, they all flunked it. Because you know you're not going to study, right? I know. There's that occasional one person who might study, but. Okay, shall we go over the first one together? Yes. Okay, since the overall space is smaller or decreasing, all particles, reactants and products collide more frequently. Therefore, both the forward and reverse rates increase. The direction with more gas molecules as reactants will have a greater increase in rate, since the concentration of gas molecules is affected more. So if you think about it, if you've got 5 gas molecules on one side and 2 gas molecules on the other side, if you squish the volume, 5 things are increasing in concentration over on the side with more gas molecules. On the side with only 2 gas molecules, only 2 things are increasing in concentration, right? So this is affected less, and the one with more particles is affected more. So the direction with more gas molecules will be faster. You could also say favored. Okay, that also works in that blank. And if the side with more gas molecules is faster, so here we have more gas molecules, and here we have fewer gas molecules. And if the direction with more gas molecules is faster, and the other direction is slower, are we shifting towards or away from the side with more gas molecules? Toward, oh, what? Away from, yes? That's okay. Away from. Now, I'm going to be honest with you. This rate explanation for gases is awful. It's horrible. It's long. It's involved. Probably I'm not going to ask you that on a quiz or a test because it'll take too long. So probably you'll be explaining it in terms of Le Chatelier. You're going to love Le Chatelier. Super easy, super fast. Okay. Now, what if we do the opposite? What if we decrease the pressure by increasing the volume? So we've taken our situation and we've decreased the pressure. The overall space is bigger. Therefore, all particles collide less frequently. Therefore, both the forward and reverse rates decrease. It doesn't matter whether I'm increasing concentration or decreasing concentration. If I've got 5 things over here and I decrease their concentration, I'm decreasing the concentration of 5 things. So that's making a bigger difference than if I decrease the concentration of only 2 things. So the side with more gas molecules will have a bigger decrease, or greater, I guess greater is a better word, greater decrease, since the concentration of gas molecules is affected more. So both rates decreased, but the direction with more gas molecules decreased more. That means the reaction side with more gas molecules will be faster or slower? Slower. And if you have trouble thinking which way is that shifting, say, okay, more gas molecules over here, fewer gas molecules over here. And the direction with more gas molecules is slower, which means the direction from fewer gas molecules is faster. And if that's the case, which way are we shifting? We are shifting towards the side with more gas molecules. What if we have the same number of gas molecules? Both rates increase, and this would be if we decrease the volume. Both rates would increase equally or the same. And there will be, if there's, it'll be equilibrium, there will be no shift. Yes, because we're still at equilibrium because the rates are still equal. So you will see a increase, or actually you will see a stress. No, you will see a spike in all the concentrations, but you will see no shift. In other words, you're going to see no curve. So it's just going to be flat. Okay? Yeah, it'll just go right angles. All right. Let's look at Le Chatelier. Do you remember Le Chatelier's principle? If a system is at equilibrium and it is stressed, the system will shift in order to minimize or counteract the stress. So if the stress was an increase in pressure, what will the system want to do? If this was our stress, what will the shift want to do? It will want to decrease the pressure. Now, let's take a look at what that would look like. Here's our container. It's got some gas molecules in it. And we shrunk the volume. Yes? So the pressure has gotten bigger. How can we make the pressure smaller again? How can the system make the pressure smaller? It's going to shift to the side with less gas molecules. I'm going to put fewer. Okay. So what'll happen is the system shifts, so it takes, 2 molecules and makes 1 molecule a couple times, and you end up with, oh, hey, now I have fewer molecules altogether. Now the pressure is come back down. Okay, so it went up. Now it's coming back down again. Now, if the stress was a decrease in pressure by increasing the volume, say we start with something like this, and we make the volume bigger, the system says, oh no, the pressure is too low. I would like to make the pressure higher again. Do I want to make fewer gas molecules or do I want to make more gas molecules? I want to make more gas molecules, so we're going to shift to the side with more gas molecules, okay, in order to bring the pressure back up. If there are the same number of gas molecules on each side, shifting will not be able to counteract the change in pressure. So there will be no shift. So you will see a spike, but no shift. In other words, no curve. Okay. So let's graph what it looks like if we have the same number of gas molecules on each side, because this is something we haven't looked at before. And by the way, if you're going to say there is no shift because there is the same number of gas molecules on each side, make sure you please include the word gas. In front of molecules if you're explaining pressure, when explaining pressure. Because if you say, if I shift to the side with more molecules, that doesn't tell me anything. If you say I shift to the side with more gas molecules, that tells me something. That's a place where lots of people lose marks on a quiz. Yes, I'm warning you, telling you right now, make sure you put gas. If you're talking about pressure, use the word gas. Okay, so if you're talking about pressure, use the word gas in front of molecules. All right, rate diagrams and concentration diagrams. We have this system here. We have H2 plus I2 in equilibrium with 2HI. These are all gases, gas, gas, gas. And here we have rate. And here we have time. And forward rate. And reverse rate. And initially these two are the same. Now my other block chose to increase the volume. What would you guys like to do? Do you want to increase the volume or decrease the volume? You want to decrease the volume? Okay, let's do it. So right here, we are going to decrease the volume. Tell your partner what you should see immediately in the forward and reverse rates. They should both go up. Do they go up by the same amount or by different amounts? How many gas molecules over here? 2 gas molecules. How many gas molecules over here? 2 gas molecules. So, do they go up by same amount or different amounts? Same amount. Okay. Now what happens? They're still equal, so they're just going to stay equal, and they're just going to continue across directly from where they were. Is it getting colder in here? Feels like there's a cool breeze. I don't know. Anyway, concentration diagram. H2 plus I2, 2HI. Actually, why am I rewriting it? It is right there. So here we have concentration. Here we have time. So the concentration increases when we decrease the volume. Does it matter how much I increase each of the concentrations? No, because remember, if I actually try to make it accurate, the graph becomes really ugly, right? So remember, you don't have to worry about how much you increase them by. Don't worry about the stress increase or decrease amount for pressure. Okay, you just say, oh, they all go up, 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 up. Don't care how much, okay? It becomes way too complicated if you start caring. Now, we have decreased the volume, and so which way are we shifting? Remember, here's our reaction right here. Why? I got 2 gas molecules over here. I got 2 gas molecules over here. There's no shift. And if there's no shift, what would that look like? They just go straight. Flat line, no shift. We are going to have a quiz on all of this stuff, 2.1 and 2.2, next Tuesday. Okay? It's already been set. I'm sorry. I told the other class already. Sorry. Okay. You'll be fine. You'll just study hard this weekend. Yes. Before spring break. Probably the Thursday. Well, if I do it before, it means we won't get to finish the unit and you'll have to write a test on things you haven't learned yet. Yeah. So, okay. All right, changing temperature. This is on page, what page are we on? 50, 51, 51. Page 51. So is the forward reaction here, so we can take a closer look at this reaction, is the forward reaction endothermic or exothermic? Exothermic. Is the reverse reaction forward endothermic or exothermic? Endo. Which reaction has the higher activation energy? So what I'd like you to do is I'd like you to think about that, maybe help yourself out by drawing a potential energy diagram. Yeah? Chat with your partner about that. So if our forward reaction is exothermic, that's going to look like this. So which reaction has the higher activation energy, the forward or the reverse? The reverse. And that is because the endothermic reaction always has the highest activation energy. Progressive reaction? I'm like, what's too small? Progressive reaction. What happens to the forward rate when the temperature is increased, and why? Chat about that with your neighbor. Okay, temperature increases. What happens to forward rate? Increases. Because when temperature is increased, what happens? The particles have more kinetic energy, yes. And they move faster. Therefore, number one, there's going to be two things. What's our first thing that happens because those particles are moving faster? We have more collisions. And secondly, we have a higher percentage of collisions which are successful. Chat with your partner about what happens to the reverse rate when the temperature is increased. Exactly. What happens to our reverse rate? It increases. Why? Same reason. Same reason. I'm not going to rewrite the whole thing. That's why I didn't leave much space here. Same reason. Okay. Now, you have a choice as to whether we go through which rate increases more and what if I explain why with the little diagram. Do you care about the explanation? Because you are not going to be responsible for these diagrams. Up to you. No, you will not see them on the test. Should we skip it?
Yes.
Okay, does anyone want to see it? If you would like to see it, I can show you some other time. Okay? because it does actually explain why the endothermic increases more, but it requires a little bit of explanation. If you would just like to believe me that changing temperature affects the rate of the endothermic reaction more, that will do for grade 12. If you're thinking, maybe I'm going to go off to university and I would like to understand it better, please drop by and see me during Flex or after school, and we can talk about those graphs on the previous page. But this might get us out of here a little bit earlier because I did it with the other block. Okay, so maybe we can finish early. Okay, I'm going to try get you out of here Friday afternoon. All right, after increasing temperature, which rate is faster, the forward or the reverse rate? Why? Because the reverse is endothermic and the forward is exothermic. Both rates increase, but the reverse rate increases more because it is the endothermic direction. So which rate is faster? The reverse rate. What is being made faster? Products or reactants? Yeah, and if you have trouble visualizing that, just draw the arrows for yourself, right? Be like, oh, that one sped up more, so I've got a bigger arrow, so I'm making reactants faster. And if I'm making reactants faster, the system is shifting left. So let's do a rate diagram for this. Rate, time, forward, reverse, forward, reverse, and here we increase the temperature. I'm just going to rewrite the equation again so you can see where the heat term is. N2 plus H2, oops, 3H2 gives 2NH3 plus 92 kilojoules. Yeah, of course. So what should happen to the forward rate? Forward rate should go up. Reverse rate should go. Uh-oh, I shouldn't have made that line so big. I'm going to run out of room. Okay, forward rate goes up, but remember the reverse rate increased more because it's endothermic. So the reverse rate should go up by more. And then I'd like you to describe to your partner what's going to happen with those two lines next. So we have the stress. Do we have a shift? Yes, got to have a shift because the rates are not equal, and shifts appear as curves. So should it look like this? Do you like that? Does that look awesome? No, that looks terrible. That's an S curve. No S curves. Should it look like this?
No.
No, it needs to be a curve, not two straight lines. Okay, so that's going to go up, and then I always kind of like to put a little dot here just to be like, that's the end of my stress, and now I'm going to shift. Okay. Is good? Okay, let's do our concentration diagram. All right. So let's start with what we've got. N2, 3H2, 2, NH3. Oh, that should be an arrow, not a plus sign. Whoopsie. Be an equilibrium arrow, not a one-way arrow. Oopsie. And our heat term is over here, 92 kilojoules. So we're going to put our N2 here. We'll put our H2 here. And we will put our NH3 here. And I would like you to describe to your partner what you think is going to happen. Okay, my first question to you, where does the vertical spike go?
Down.
Which of them? And it's a trick question.
Down.
Where does the vertical spike go? Nowhere. Temperature does not change concentrations. Whoops, I should have said this is an increase in temperature, but I thought we just remembered from last time. Okay. So, no change in concentration. So I will not see any vertical spikes in a concentration diagram when we have temperature. Okay. Who is going to go up? Who are we making faster than we're using them up? We are making reactants faster than we are using them up. So concentration of reactants will go up. N2 will go up. H2 will go up by how much? The same amount? Got a coefficient 3 in front of the H, so it's going to go up by 3 times as much. 1, 2, 3. Woo. 3x. Okay, and then the NH3 is going to go down by, I'm sorry, that's a 2 there. It's really hard to see. It's going to go down by 2x. 1, 2. And you see my 2x looks kind of like my x. It looks like more like a 1.5x. So that's why I label them, because I don't always do a good job at drawing proportionally. Okay. Okay. We got 2 more pages to get through. Can we do it? We can do it. Okay. Le Chatelier's principle, we're not going to write it right now because we want to get through this. Yes? For homework, you're going to write Le Chatelier's principle. All right? Because it's important that you remember how to write it, that you know what it means. So, in the reaction, would you like a cough drop? You're good? Okay. Because I think I've got one in there in my drawer somewhere. Yeah. Okay. Let me know. In the reaction in the forward reaction, in the reaction above, the forward reaction, does it absorb heat or release heat? The forward reaction releases heat. Yeah? Now, don't make me a liar. Oh, come on. Am I a liar? Oh, I'm a liar. Oh, shoot. I can't help you. I'm so sorry. I must have used the last one. That's frustrating. Okay. The reverse reaction, does it release heat or absorb heat? Absorbs heat. If we decrease the temperature, the amount of heat in the system so if we decrease the temperature, the amount of heat in the system, has it increased or has it decreased? We decrease temperature, heat has decreased. So our stress is a decrease in heat. According to Le Chatelier's principle, the system will shift in the direction that, now, does the system going to want to release heat or absorb heat? Let's think about the second part. In order to bring the temperature back up, so if we want to bring the temperature back up, what does the system have to do? It has to release heat. Yes? So if we decrease temperature, the system needs to shift to release heat. That will bring the temperature back up. And in that case, the system is shifting to the right. That kind of walks you through it, but if you want it to be even simpler, you can say decreasing temperature favors the stupid pen. Exothermic reaction, since it releases, oh my God, give me 5 more minutes, you little pen, okay? Since it releases heat to bring the temperature back up. This is all you need to say for Le Chatelier's principle. Increasing the temperature favors the endothermic. Now, this is nice. Look, in, N, in, N, in, N. Increasing temperature favors the endothermic reaction since it absorbs heat, which will bring the temperature back down. I don't think we need to do a rate diagram and a concentration diagram. We just did one, right? Okay, so we're not going to do that. And I actually assigned this for homework to the other block. because the bell rang. So it's up to you. Do you want to go through this together, or do you want this to just be part of your homework? You want to do it together? Okay, let's do it quickly. Explain the following shift in terms of Le Chatelier's principle and in terms of rate. Stress, we decrease the temperature. Oh, watch this. Do you remember our arrows? We decrease the temperature. You can put an arrow above the heat. And then you can draw your shifting arrow so that it goes over top of the equilibrium arrow. Yes? And where does the arrowhead go? Goes to the right. So that then becomes a really quick way to predict if I decrease the temperature, it shifts towards the heat term. Yes? So Le Chatelier says the temperature was decreased. The system is going to shift to the, in this case, right, in order to release heat, to bring the temperature back up. If you're going to explain it in terms of rate, a decrease in temperature, what does it do to both the forward and reverse rates? Decreases both the forward and reverse rates. But a change in temperature affects the rate of the always endothermic reaction more. And since the endothermic reaction in this case, here's our heat term. Which direction is endothermic, forward or reverse? Reverse. Okay, so therefore, we have decreased, and I like to draw my little arrows because then I can say, okay, both rates decreased, but the endothermic reaction decreased more. So this one decreased more, this one decreased, but it decreased less. Yes? So that tells me that the rate of the forward reaction is greater than the reverse reaction. Therefore, and you can just look at it and you can say products over here, reactants are over here. That means my products are being made faster than the reactants, which means the system is shifting right. Me too. I don't know. I have trouble with left and right, up and down. No, up and down is okay. But anything left and right, like east and west, can't do east and west. Like, especially if I go somewhere where the ocean is on the other side. Like if I go to the East Coast, I'm like, oh, west. It's where the ocean is. Okay, do we need to go through the opposite case? Yes, okay, the temperature was increased, so the system shifts left. Oh, what happened? I reversed the reaction? Oh, it's a different reaction. Okay, different reaction. The system is going to shift left in order to release heat to bring the temperature back up, because here's our heat term. It's a different reaction now. I know, it's just a different reaction, different example. I know, it surprised me too. The increase in temperature increases both the forward and reverse rates. A change in temperature affects the rate of the...
Wait, wouldn't you bring that temperature back down?
Huh? Where? Oh, where? Oh, this one should be back. Down. Down. No?
The other one. So next, the second one, is the temperature one,
Uh-huh. Down, down, down. Friday afternoon. Sorry, Friday afternoon brain. Which what? Oh, we should absorb heat. See, you guys didn't want me walking you through this. This is a disaster. I am so sorry. Oh my gosh. At least I got the left correct. Holy mackerel. I could say I was doing it to make you think, ha 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 ha, but I would be lying. Okay. The increase in temperature increases both the forward and reverse rates. A change in temperature affects the rate of the endothermic reaction more. Therefore, the rate of the endothermic is forward reaction is greater than the reverse reaction. So forward is greater than reverse. That'll just help me to say what's happening with my reactants. Am I making them, which one am I making faster? I am making products faster than reactants, so the system is shifting to the right.
System shifts.
Oh my God, what is wrong with me?
Everything else.
I'm just so mad. I'm so sorry. Oh my God. Okay. So, we will talk about this determining if the reaction is endo or exothermic on your next thing. Your homework is pages 46 to 49, 54 to 56, and study all the other stuff from the other sections because you have a quiz on Tuesday. Dorsa, Hannah, come talk to me for a second because I've been thinking while I've been teaching. No, obviously.